So anyone that's watching this later, if you're not watching this live, you can just skip forward maybe 2 minutes or 3 minutes after the start of this audio, and we'll get into the actual presentation. So the key thing to mention here, though, is that this is a shortened version of the traditional Skywarn course that we typically give, where we will go out to different communities and give these talks during the spring. Mainly because we've all been a lot of us have been working from home for more than a month now, and it's hard to keep attention when you're going on for an hour and a half or 2 hours. So we tried to keep this one to an hour. We really get to the main points. But really, if you're interested in learning more about storm spotting, or getting one of our official spotter numbers, we hope you attend one of our in-person courses whenever we're able to schedule those again. So again, we're gonna try and keep this around an hour. Questions, you can type into the window there on Facebook Live, and we'll have a meteorologist answering those as we go. So feel free to ask any questions you want at any time, and we'll get a response to those fairly quickly. Okay, it's 7 p.m. I'm gonna get going now. So good place to start is what is the role of storm spotters? Why do we need storm spotters? Why are we spending time here on a Tuesday night to watch someone sit on his couch and talk about thunderstorms? Well, storm spotters are an essential part of our warning operations. When we're putting warnings out on potentially dangerous storms, we can't just look at radar. We can't just look at satellite and all these other high-tech weather tools we have, because all those tools have limitations. Satellite is up there way out in space. It shows us the top of storms really well, but it doesn't show us the bottom of storms, which is where tornadoes, hail, wind, heavy rain, all that happens, the bottom of the storm. Radar has the same limitation. This picture here, our radar, one of its limitations is its beam is always getting higher off the ground the farther it gets from our radar in Chanhassen, Minnesota, on the southwest side of the Twin Cities Metro. So, if we're in the Twin Cities Metro within, 20, 30, 40, 50 miles, we've got a pretty good view. Our radar's looking maybe down here. But when we get out 50 plus miles, even with some tornadoes, they're not that tall. So, it's hard to see the lowest part of the storm when we get farther from the radar. We might be seeing a lot of rotation up here, but we see nothing down at the ground, which is where spotters come in. They're essential, right? They're our ground truth. They're telling us exactly what is happening on the ground. So in the office, we may be watching a rotating thunderstorm, possibly producing large hail, damaging winds, or even tornadoes. This is what we see at the office, but what we're seeing on our radar image, that image might be a couple minutes old. Radar's never live in real time. There's always at least a minute delay before we see the images. We might also be looking 5, maybe even 10,000 feet off the ground, and we just have no idea what's happening at the ground. But spotters, like I said earlier, can help us fill in and get that ground truth on what's actually happening in real time on the ground. Storm spotters, they give us real information. They can let us know, hey, a tornado is on the ground right now. We usually can't tell if a tornado is actually on the ground doing damage on radar. Only if it's really close to the radar can we see a signature that might suggest that. But if a storm spotter calls us with a report of a tornado on the ground, sends us a picture like they might on a Twitter post here, we can share this with people. People take action, or more likely to take in threat as serious if they perceive it as being real. So if you see a picture of a tornado, and maybe it's the next town down the road from where they live, they see that picture, they're way more likely to take shelter versus the robot weather radio voice or some of the alt text you might see in one of our classic warnings. So when we're able to get a real human confirmed tornado, and especially pictures, it really leads people more likely to take action from and sheltering during severe weather. So again, spotters are just one of many tools that we use to put out the best warnings that we can. The more of these tools we have working for us, the more accurate warnings we can put out. Hopefully, more lead time on our warnings to get people to safety faster. We can't just rely on radar or satellite. We need everything. Can't just rely on spotters either. If we just had spotter reports, we wouldn't be able to maybe get as much lead time on a storm as we might with radar or satellite, being able to see what's happening higher up in the storm. So kind of the overview of what we're going to go over tonight. Really, it's going to be a lot of looking at storms. As you're a storm spotter, you're hopefully looking at storms. And by identifying a couple key features on different parts of the storm, you're able to kind of judge the strength or potential of that storm and what kind of severe weather it might possibly have the potential or chance of producing. Once you've looked at a storm and maybe see something that's worth reporting to us at the National Weather Service, well, you're going to want to make sure you're safe. Make sure that storm's not moving right at you. You're in a safe spot. And then ultimately, again, give us your information. If a tornado happens in the middle of a field, but you're the only one to see it, and don't tell the Weather Service, well, it doesn't help us too much. So we'll get into how to give your reports to us, and there's multiple ways to do that. So updrafts and downdrafts. Every storm has one. Your typical summertime 30-minute garden thunderstorm or a tornado-producing supercell. Every storm has an updraft and a downdraft. The updraft is the warm, humid air that feeds into the thunderstorm. What that looks like if you're watching a storm, well, that's going to be your clouds. Your thick, puffy, billowy clouds you see on a summer day. That's your updraft. That's where that warm air is feeding into the storm. Your downdraft, where that air eventually has to sink back down towards the ground, that usually is where the rain's coming out. That rain is heavy. It pulls down air as it falls. Some of it evaporates as it falls. It cools the air, and that cold air is heavier. And so that leads to a lot of rainy, colder air rushing out underneath the storm. This is often where we'll see the strongest winds in the storm and hail as well. So it's kind of the interaction between these two that's crucial in what kind of thunderstorm we have, how strong it might get, how long it might last, what kind of severe weather it can produce. So just kind of showing you every thunderstorm follows the same life cycle. Starts as an updraft, just some kind of summertime billowy clouds. If we have the right ingredients in place, that cloud grows into a full mature thunderstorm. You see where air is rising in the updraft here. Eventually it basically can't rise anymore. It can't go all the way out into space, so it has to sink back down eventually and brings rain down, hail down, wind down with it, and then falls back out a different part of the storm. So we have a nice updraft region, usually a clear part of the storm, at least underneath it. We have a dark, rainy downdraft region where all that hail or rain, but maybe some hail is coming out. Eventually, this downdraft region wins out. All this cold, rainy air cuts off the warm, humid air feeding into the storm in the updraft, and the storm dissipates. All right, so this is kind of a schematic textbook image of the thunderstorms we're going to be really focused on tonight, what we call supercell thunderstorms. These are the thunderstorms that rotate. When a storm rotates, it's able to get a stronger updraft. A stronger updraft means a stronger storm. And also when a storm rotates, it's able to produce, kind of what we're most interested in putting out warnings, at least the most damaging part of a thunderstorm, tornado. So kind of, it's kind of a textbook image here, but you can see on the left side of that storm, kind of a clear part over here. That's our updraft. That's where warm, humid air is feeding into the storm, kind of making littler clouds and then bigger clouds, and eventually feeds into the main thunderstorm updraft here. Think of your thick, billowy, puffy, white clouds. That's a lot of rich, warm, humid air feeding into that storm. Eventually, that air has to stop rising, so it'll spread out for a bit and then sink back down to the ground. So if you ever wonder why a thunderstorm has an anvil on it, that air stops rising in the updraft, it spreads out, and then eventually sinks back down to the ground there, brings the rain, hail, and wind down with it. If it's a really strong thunderstorm and you're far enough away, you might see this bubbly top on top of the anvil. We call that an overshooting top. And it usually means we have a stronger thunderstorm we're dealing with. It just means that updraft is strong enough where the air is rising. It actually punches through the stratosphere where this thunderstorm updraft spreads out eventually, and punches through into the stratosphere a little bit before sinking back down. Typically a sign of a stronger thunderstorm. Doesn't guarantee a tornado or damaging wind or hail or anything like that. But again, we're not always going to look at split storms, so we'll show a couple of real-life examples here. First example, kind of boring. This is kind of your classic early stage of a thunderstorm updraft. Note the kind of bubbling clouds here just starting to go vertical, opposed to the kind of flatter, fair weather clouds around it. And all you're seeing there is the first stages of that warm, humid air starting to rise, starting to form an initial updraft. And if all the ingredients are in place, continuing on into a thunderstorm. What we want to note here, though, is the flat base. Notice the flat bases on all these clouds. I mean, every cloud typically is going to have a flat base to it, but you'll see these thick, kind of towering, billowing clouds, thunderstorms even. But underneath it, you'll see this flat base. We call that the updraft base, and that's where that warm, humid air is first rising enough to form clouds and really start feeding into the thunderstorm. A common theme in this talk will be to watch whatever feature you're looking at. Don't just take a picture out the window and give us a report. Watch how all these thunderstorms evolve, because it might not look like much right now, but give it 20, 30 minutes and you've got a fully mature thunderstorm. Again, just note how the clouds look, right? Typical summertime thunderstorm. Thick, puffy, billowy clouds, sharp edges on all the cloud features, which is a good sign that you were dealing with a lot of moisture. Notice how the anvil is really sharp compared, just sharp cutoff between the edges of the cloud anvil and the blue sky around it. Those are all signs that typically we are dealing with a healthy thunderstorm, a thunderstorm that's probably not weakening anytime soon. Now, compare that thunderstorm to this one, if we can even call it a thunderstorm. Just doesn't have the same structure to the clouds. They're not quite nearly as billowy, puffy, kind of rigid and organized. Note the fuzzy edges on all the anvils up here. That's signs usually of a weaker storm, or a storm that's starting to weaken. Now, the storm could weaken and then re-intensify and go through a couple cycles. That can happen. But just kind of at a glance far away, you might be able to judge the strength of the storm, just kind of how the clouds look. We've all seen thunderstorms, the really, strong, healthy-looking ones, and some of the kind of messier ones. Maybe this time of year, early spring or mid-spring and into the fall, you get kind of these little bit messier looking, maybe not quite as intense thunderstorms, at least in this part of the country. So we kind of just mentioned all that, just a quick overview slide here. Again, you can't, there's better ways to judge the strength of a storm, radar being the best one, but just by looking at it, you can kind of tell the general health of the storm you're looking at. Is it a healthy storm, or is it a storm that's maybe on the starting to weaken and maybe trending down? Maybe the severe threat's getting lower with it. Now, those first examples were from pretty far away. We want to get closer, zoom in, see the bottom of the storm. So that's where all the features come, all the features coming out of: hail, tornadoes, wind, all that. So this is what the updraft, downdraft looks like underneath a storm. Again, note the flat updraft base right here. This is where all this air is feeding and rising into the storm. And then note the rainy, dark downdraft region where the air is coming back. Notice how they're kind of next to each other, interacting with each other, but they're not cutting into each other. If that were to happen, it means the downdraft's going to cut off the updraft and the storm is going to weaken, or maybe in the process of weakening. We want to see separation between these two, but maybe not too separate, especially in terms of tornadoes, which we'll get into here coming up. But just note the contrast between the two regions. Flat updraft base, clear, dark and rainy. So here's our first video here. We have a couple of videos scattered throughout the presentation. So this is a great example of, if you're spotting a storm and you're at a safe distance, you're not right underneath it, but you're still able to see all of the relevant features. And just to note the updraft region of the storm and then the downdraft region of the storm. Pretty obvious, right? The flat updraft base here, clear part of the storm. We can see the sky behind it. And then right next to it, the dark rainy storm. This air is rising all in through this region, feeding up through the updraft. You can kind of see some of the thicker, billowy clouds up here, and then eventually sinking and falling back down in this region. Now, if you have a sharp eye, you might note this other cloud feature hanging off of that updraft base. That's a sign we're dealing with a rotating thunderstorm. It's called a wall cloud, and coincidentally, we'll be talking about that right now. So wall clouds, you may have saw that on the schematic earlier. Basically a sign that we're dealing with a rotating thunderstorm. It typically is it's a marker for where the strongest rotation and the best inflow, the best warm humid air feeding into that thunderstorm are located. If this is a rotating thunderstorm that is strongly rotating and maybe has some tornado potential to it, you'll see those clouds actually spinning underneath the updraft base. Typically, you'll see in a counterclockwise manner. This other cloud feature hanging off the bottom of the updraft base will be rotating and maybe even getting lower to the ground with time. And those are two signs that maybe we're making the first step towards a potential tornado here. If it's going to tilt one way or the other, it will usually be tilted towards the downdraft region, the dark rainy part. It may be symmetrical, it may be tilted a little bit towards the downdraft area. So here's one of maybe the best wall cloud pictures I think I've seen. You can almost visually see the rotation, kind of how this air is corkscrewing upwards as it rises into the updraft region. But like we just said, air kind of feeds in here from all directions, rises up through the updraft, rotates in this case, and then eventually comes back down in the dark rainy region over here where the downdraft is located. And then again, we have our flat updraft base just like any cloud or thunderstorm, but we have this additional cloud feature hanging out underneath it, rotating if it's a visibly rotating if it's a storm exhibiting strong rotation. But again, we're not always going to be dealing with textbook ideal thunderstorms here. You know, not every thunderstorm produces a tornado, luckily for us. So this is maybe more typical of a common wall cloud you'll see here. Again, this is kind of flipped. Most of the pictures we've seen, the updraft on the left, the downdraft on the right. This is opposite. But no, again, flat updraft base right here, clear for the storm, dark rainy downdraft over here, and then just note this little feature hanging off the updraft base. That's a wall cloud. Not nearly as impressive as the first one we saw, but again, they're not all going to be your textbook thunderstorms. Now, the main key to watch is you can't just look at that picture and say, oh, it's weaker than the other one or stronger than the other one. Really, what kind of tells us the strength of our thunderstorm, how strongly it's rotating, is being able to see rotation, visible rotation in that wall cloud or in the updraft region of the storm. So that's really what you want to be watching, the updraft part of the storm, trying to spot that wall cloud if the storm has one, and identifying any rotation. Is it speeding up? Is it slowing down? How fast is it? If you just see a wall cloud that sits there and doesn't spin at all, that thunderstorm's rotating just to have a wall cloud in the first place, but it's probably not nearly as imminent to produce a tornado as one where you look at it and that wall cloud is just spinning like crazy. You can just see it with your naked eye very easily. How low is it to the ground? The lower that wall cloud gets, typically the maybe closer we are to producing a tornado. Sometimes you'll feel that wind if you're watching the storm. You'll feel the warm, humid air feeding into the storm at your back, and if that you suddenly feel a strong increase in that air feeding into the updraft, that's a sign the storm is potentially or is increasing in strength and maybe closer to producing a tornado or more severe weather. And then eventually, if you have a rotating wall cloud and you've been watching it and the rotation getting stronger, you may start to see the first signs of a funnel cloud coming out of the bottom of that wall cloud or the bottom of that updraft base. So first video here of a wall cloud at least. Kind of your textbook looking wall cloud hanging off the bottom of the updraft base. You can see it here. But notice in real time, you don't see any rotation in that wall cloud. If you're watching it, you don't see these clouds, moving from left to right or spinning underneath this updraft base. They're just kind of sitting there. So it doesn't mean the storm is something to forget about, but it's maybe a bit longer and see if that rotation increases before we'd see maybe a heightened tornado potential, at least within the next few minutes. Now we've sped it up, I think 6 times here, and you can see some more rotation now, especially up in the updraft region, but we don't see a ton of crazy rotation in this wall cloud, even at 6 times sped up. So, not going to expect a tornado out of this one probably in the next minute or two, but certainly something we need to keep watching. So, how do I know if I have strong rotation that maybe I'm really concerned about a tornado? Well, it's obvious. If when you see it, you'll know. When you watch a storm, you will know if there's strong rotation present. I know that can be kind of hard for some of you that have maybe taken this training for the first time, have never seen or even heard of what a wall cloud was before this. We'll show a video example nets of some really strong rotation, but you'll see those clouds and they will be visibly rotating or visibly moving from left to right or right to left underneath that updraft base. And again, make sure you're watching the updraft base, but also you're watching for rotation along a vertical axis. So something that's, basically imagine a line pointing straight up, it's going to be rotating around that line. Not a horizontal axis, not, can't see my fingers spinning right now, but, not clouds that are kind of rotating sideways, if you will. They'll be rotating along a vertical axis pointing up through the updraft base. So here's an example of some very strong rotation. Again, they're not all going to rotate this strongly, but this was the 2010 tornado outbreak in southern Minnesota. But, you just watch this wall cloud here. First of all, it's massive. It's huge. And just see how strongly those clouds are moving left to right underneath the updraft base right here. Also note how low this wall cloud is to the ground, and it gets lower with time. Note the strongest rotation right in this region here. And then I think the little bar covered it. Sorry about that, but you could see just how quickly that tornado formed. Almost out of, you didn't see really any funnel at all. It went straight from a rotating wall cloud right to a tornado. And that's why we really, really appreciate all the reports you can give us of a rotating wall cloud. The non-rotating wall clouds, probably watch it for a bit longer, see if it starts to show more of a tendency towards some stronger rotation. But when you watch a storm, you see the wall cloud and you see that visible rotation, those clouds pretty clearly moving from left to right or right to left underneath that updraft base. That's a report we want to get, because sometimes we don't get the nice transition between wall cloud to funnel cloud to tornado, like we saw in that tornado right there. So we can get a lot of lead time on warnings if we get reports of these rotating wall clouds, visibly rotating wall clouds. So again, leading to our next subject here, tornadoes. So tornadoes are a rotating column of air, rapidly rotating. It's not the funnel, it's actually just a column of air that spins, and through those processes eventually will produce a funnel cloud that may or may not reach all the way down to the ground. So typically, again, we'll first see this tornado on the ground as rotation or debris. We'll see some dirt or maybe some damage being done right at the ground, while that funnel might still be, halfway up above the ground. That's actually fairly common. And then typically we go rotating wall cloud. Wall cloud starts to rotate faster. Maybe we see that lowering of the wall cloud. We see a funnel cloud form, and then we see the tornado circulation on the ground. But again, sometimes we go really fast through some of those steps. It's not always a nice, clean, linear process. So a couple of pictures here. Is this a funnel or a tornado? Well, we're definitely a funnel. Here's our updraft base. Here's our wall cloud right here. And then we have this funnel, again, out of the center of the strongest area of rotation under that wall cloud. But if you look at the ground, you can't really see. I don't see any dirt being picked up or even bits of trees. I would call this you have to call this a funnel at this point. We definitely want reports of funnel clouds, but hold off on calling this one a tornado until we see obvious evidence of that circulation doing damage or picking up debris on the ground. Fast forward a little bit longer, and still see the funnel right here, but now we see our first signs at the ground. Maybe just the first seconds of some dust being picked up by that tornado circulation. We can see our first signs of this is actually a tornado on the ground. There's actually debris being picked up right at the surface. Even though our funnel is still the same distance, about halfway, only halfway between the wall cloud and the ground. Now, fast forward a few seconds or a minute later, we're starting to get more of a typical looking tornado. We see more debris being picked up at the ground, and then maybe the tip of that funnel is hitting the ground there. But again, this whole circulation is this big. The funnel is just a side effect of the tornado circulation. So it's really what's going on at the ground here is what we're most concerned about. And then again, a few minutes later, we have kind of our traditional stovepipe tornado where the funnel is totally connected to the ground and basically forming the whole tornado circulation there. But that didn't happen immediately. That was a process that took probably a few minutes for that full kind of traditional looking tornado to form. This is another example here. Is this a funnel or a tornado we're looking at? Well, again, we definitely have a funnel, kind of at least the first signs of one up here, but nothing below it at the ground. So kind of to reiterate that same point here, the tornado is a circulation of rapidly moving air, rapidly moving column of air. So it's not the funnel. The funnel's a side effect of the tornado circulation. And we're really looking for any sort of indicators at the surface that column of air has made contact with the surface. Dust, debris, maybe potential damage to structures as well. So this isn't a tornado video festival we're having here, so we don't have a ton of videos of tornadoes, but this one's a good kind of example of a typical life cycle of a rotating wall cloud to funnel cloud to tornado you might see. So again, note the wall cloud there. We're really close, so we can't see much of the updraft, but you can visibly see that rotation right off the bat. Very obvious those clouds are moving from left to right in that wall cloud. That is obvious rotation. That's strong rotation that we want to know about as a report. You see that other cloud feature underneath the wall cloud? Maybe it's the start of a funnel or more of a sign that we have a lowering wall cloud there. But now, fast forward a little bit, we do have a funnel cloud visibly rotating, but look at the surface, maybe right about now is our first signs that we have some actual debris being kicked up at the ground. The funnel's still up here, but you can see really now all this dust being picked up into the tornado circulation there. And finally, we step forward a bit and we have kind of the end of the tornado here. Just because it looks skinnier and not as maybe as impressive does not mean those are weak winds in that tornado. Really, the size of the funnel doesn't really tell us a lot about how fast winds are, how damaging the tornado may be. Typically, though, we will see that as a tornado begins to weaken or get closer to ending, it will tend to get a little bit skinnier and stretched out. We call it roping out. Then the key is to watch and see if maybe the storm recycles and other tornadoes may form after that. And kind of the last part on tornadoes here is your viewing angle matters. We'll talk about where to put yourself ideally to spot storms in a couple slides. But, we're going to show two pictures of the same tornado here. And on the left, there's a definite funnel, but you can't really see the ground. There's some trees behind, trees blocking our view. We can't see what's going on at the ground. This is a funnel from this point of view, but maybe other side of the storm here, you actually can see right down here some dust being kicked up underneath that funnel cloud, showing us that circulation is on the ground. It is a tornado. So basically, don't guess at what you're seeing. Just tell us exactly what you're seeing, because maybe someone has a different vantage point on the storm than you do, and we can kind of piece together the whole puzzle by using those different viewpoints. Okay, so that was the updraft part of the storm. Usually easier to see features there because then it's clear. You can actually see the bottom of the updraft base and any potential rotation or wall clouds, funnel clouds, tornadoes that come out of that. Now we're going to focus on a couple of downdraft features. Remember, every storm has an updraft, the warm, humid air feeding in to that storm, and a downdraft, the rainy, dark part of the storm. Yeah, and so it's the balance between those two that kind of determines what kind of storm we're dealing with, how strong it might be, how long it might live, what kind of severe weather it might produce. And as we can see there. So here's kind of a good example of just a nice, kind of almost uniform downdraft here. See the dark, rainy part of this storm here. It looks like it may very well be punching through the updraft base of this storm, which might be a sign that this is maybe the last gasp for this storm. It's kind of putting out all its big downdraft now and will eventually be weakening after that. But notice you just have the big, sorry about that. We have the rain coming out of the storm here. That brings a lot of, rain pulls air down with it. It evaporates, which cools the air, makes it sink faster. So we have a lot of wind, air rushing out of this downdraft. Once it hits the ground, it can't go into the ground, so it has to spread out in all directions. And you can see kind of how the dust is being blown to the left here and maybe out to the right on this side. Typically, it can be some maybe damaging wind gusts with stronger thunderstorms. Again, the stronger the updraft, the stronger the downdraft's going to be. So we've all experienced downdrafts. Think about, if you're watching a storm on a summer day and you get that cold gust of wind right before the rain starts, that's a downdraft you're feeling right there. But again, you can't look into the storm here, the downdraft part of the storm here, and tell how big the hail is in there, how strong the winds are in there. You're just going to see a curtain of black or maybe even, bluish green color. So, you don't really know what's in the downdraft till you're inside of it, but then you're hopefully taking shelter because it's the dangerous part of the storm with all the wind, the hail, everything. One key we can use on downdrafts, though, is a feature a lot of times they will develop if they're able to merge together. The more downdrafts are able to merge together, the more they're able to interact. Maybe the stronger winds we can get with this storm. So sometimes there are a lot of thunderstorms form together into maybe a big line if we have the right conditions in the atmosphere. And they all form one big linear downdraft. And at the leading edge of that downdraft, if it's strong enough, it can produce a long linear cloud feature that we call a shelf cloud. And we can kind of see that right here. This long linear, just one long line of clouds at the leading edge of our downdraft. Remember the dark, rainy part of the storm in there. The wall cloud, if you remember, was pretty compact, attached to the updraft base, and typically rotating or staying in the same spot. If you watch the shelf cloud with time, you'll just see this whole area advancing towards you in a straight line. There won't be any rotation about a vertical axis with this cloud. Now you may see some horizontal rotation where it's kind of billowing ocean wave almost as it moves along, but that's that horizontal rotation, not the rotation along a vertical axis that we're looking for in a updraft region of a storm or a wall cloud. So typically the kind of thunderstorm complexes that give us these shelf clouds, we call them squall lines. Basically, it's when we have the right conditions in the atmosphere for thunderstorms to kind of merge together, at least merge their downdrafts together and form into a big line. These can be hundreds of miles long. This one goes from Iowa all the way into the Upper Peninsula of Michigan there. But because of how these thunderstorms organize together and kind of merge together, typically the downdrafts can get stronger than one thunderstorm might just have on its own. And so really we're worried about damaging wind when we see these squall lines, or a shelf cloud maybe with one of these squall lines is a sign that, we might be dealing with some, can't say exactly how strong, but maybe some damaging winds with this storm. Maybe you've heard the derecho before on the news, on TV. We've used it. Derechos are what we call, the most intense of these squall lines. They're typically more compact than this one is. Maybe it's only something like this long where we have the strongest winds instead of this whole long thing. But these derechos can have winds 80 to 90, but even over 100 miles an hour over a large area. These last for hours, can cover multiple states. So if you hear that term ever, it means we're dealing with a more serious or severe, maybe squalling than we normally see. And then rarely, very rarely, we can get tornadoes embedded in these long line of storms. Again, the vast majority of the time we're worried about a damaging wind threat. But if we have kind of the right ingredients in the storm, we are able to get a little bit of rotation in these, that vertically oriented rotation that can lead to a few tornadoes. Typically, though, these are pretty short-lived. They're almost always wrapped up in the rain, so it can be really hard to spot these as a storm spotter. So again, our main picture of a shelf cloud here. Again, just note the very long linear cloud feature. These things will cover the entire horizon. Again, it's a downdraft feature, right? So this is the dark, rainy part of the storm right here. And along the leading edge of that downdraft, we have this long linear cloud feature. And this is going to be really moving all in one direction as that downdraft rushes out away from the storm or moves with the storm. Now, like we said, all storms need to have an updraft and a downdraft. Can't just have one. So, where is the downdraft with this storm? If downdraft, let's say it's covering everything, well, it actually, in this case, will kind of be what forming the cloud really. It kind of comes up in, it comes up and over this downdraft, the surface here, and can feed in this way. It's kind of why we get this slanted feature to the updraft, or it may even come from higher up off the ground into that storm. Now, if we don't have that updraft coming from off the ground, we can't get a tornado, because a tornado is formed from a rotating updraft, and if the updraft is coming into the storm from 1,000, 2,000 feet, it could be spinning a lot as it's rising, but it never is going to touch the ground. It's never going to form that tornado circulation. And that's why we almost always see just a damaging wind threat with these, and not tornadoes, with these long linear squall lines and if you see a shelf cloud. Again, not always. Sometimes you get little pockets of enhanced rotation. Sometimes you might have a rotating supercell thunderstorm that we showed earlier that can embed itself in a line of storms. And obviously that's where you'd probably see a tornado warning on a line of storms in a sea of a lot of severe thunderstorm warnings. But the vast majority of the time when you see a shelf cloud like this, we're expecting a damaging wind threat. So video time lapse here of a shelf cloud. Sped up 4 times, so it's not going to move this fast in real life, but we can't sit here and show it for 20 minutes. Just note how this long linear cloud feature basically covers, really the entire horizon, and it's all moving in one direction. It's all advancing from right to left in this case, moving towards us. Note the dark, rainy, downdraft back in here, and how this shelf cloud is at the leading edge as that cold, rainy air hits the ground and then rushes out. It forms this long linear cloud feature along it. You might see some, straggly clouds underneath the shelf cloud here. They might even look like they're trying to rotate or spin one way or the other. But remember, you're looking at the downdraft region of this storm. If we were worried about any sort of wall cloud or rotation, we'd be looking at the updraft region of the storm, and any of these rotating clouds would be attached to the updraft base. So we call them scary looking clouds with some of these thunderstorms, where they might look almost like a funnel hanging off of cloud feature or a shelf cloud, but if you watch it for a few minutes, you won't see any of that vertical rotation with it. It probably won't be very persistent. It might get ingested up into the storm. And again, it's not attached to the updraft base. It's a downdraft feature along the shelf cloud there. So just kind of a quick overview of wall cloud versus shelf cloud, right? Again, wall clouds, updraft features, the warm, humid air feeding into the storm. That air rotates as it rises, so it's rising on this vertical axis, and it's rotating typically counterclockwise around that. Why do we care about wall clouds? Well, they're rotating, and if they keep rotating stronger and stronger, it could eventually produce tornadoes. Shelf clouds, like we just looked at, those are downdraft features, the cold, rainy air that rushes out from the storm. These are going to, again, form at the leading edge of that outflow, that downdraft, and may exhibit some horizontal rotation. So, not oriented vertically. Not like you don't see many straight sideways tornadoes like this, at least coming out, sideways from the storm. So that's kind of your key right there. Wall clouds, any tornado potential, updraft feature, vertical rotation. Shelf clouds, if they do show any kind of spinning clouds, will typically be in the horizontal direction. But these are just going to mainly just move in one straight line with the downdraft of the storm. Typically, you're going to have your strongest winds with that storm right as the shelf cloud passes overhead. So, that was kind of our quick go around at watching storms. Our full version, we look at more examples, strong examples, weak examples. But now we're getting kind of the most important part of the talk, right? Being safe as a storm spotter. Your situational awareness is key. You have to know where you are in relation to the storm, where the storm is moving. Is there another storm coming up behind you that maybe you're not paying the most attention to? Are you in a safe spot? Hopefully, if you're at home, you're okay. But if you're out, in your car, outside watching, you might need to find a safer shelter. And then if you are out away from home, do you have a escape route? Or if you are at home, do you have a safe place to go in case of a severe thunderstorm or especially a tornado? So first off, where's the storm going? We really need to know where the storm's going if we're going to feel confident in our safety when we're watching it. Generally, they're going to move from west to east in some way or form. It might be northwest to southeast. It might be southwest to northeast. But typically, our strong to severe storms are going to move some sort of west to east motion. Supercells can be a little weird. They can actually kind of form their own deviant motion, kind of move their own way compared to the other storms. But that's really where you want to you can see that on radar, watch how our warnings are oriented. When we put out our warnings, you might see a bot's kind of oriented differently from the other ones, and that's the sign of that deviant motion. But there's multiple ways to determine storm motion. Radar is the best way to use it, but we also will put which way the storm's moving in our warnings we put out. And then you can also watch a storm visually to get an idea of if you're in a safe spot or not, just by where you are in position to the other features. So we've all hopefully seen radar on a storm spotter talk here, but just the best way to tell which way storms are moving and also, maybe how intense they are. The main key, though, these are both, this one on the right is a classic rotating thunderstorm. Supercell Thunderstorm produced the Moore, Oklahoma tornado back in 2011. So you can just see, or is that, 2013, sorry about that. You can just see the rotation around as this storm moves off to the east, just how all this is spinning. Have you ever heard of the term hook echo before? That's what you're looking at right there. That's the strongest rotating part of the storm, where that updraft and downdraft are wrapping around each other, interacting with each other, and ultimately forming a tornado. But just look how messy this radar image here. They're not just going to be one storm you're watching. There's going to be storms all over the place. So if you're down here trying to spot a storm, you've got to keep an eye on everything that's around you and moving your way. It's not just a storm you're spotting or looking at. So radar is really, really useful to just know your situational awareness. Where you are in comparison to the storm you're watching, where it's moving, and then what might be coming behind it. Again, if you don't have radar, hopefully you do. We have radar at the National Weather Service, which we use strongly to put out our warnings. So in every warning we put out, We'll draw bots around the main area of interest. In this case, we drew a tornado warning around these bots here. Notice it doesn't cover the whole storm. It just covers this hook echo where the updraft, this clear slot, is feeding into the storm, and this downdraft, the dark rainy part, is wrapping around it. Kind of at the tip of the hook here is where we expect the tornado. And our bots is just focused on that area. We're not worried about tornadoes up here. But you'll see in the warning where the storm is and where it's going, moving east at 35 miles an hour in this case. So if you were spotting this, ideally you're not right here. If you are right here, please owe your basement immediately. But, you know, maybe if you're down to the south of the storm or southeast of the storm, you'd be able to look at this hook region, this downdraft updraft interface, and it'd still be at a safe spot compared to the motion it's moving. We'll go into that in a couple slides. Just watching a storm can give you clues. Note the updraft region of the storm here. Nice, solid, you know, thick, towering, billowy clouds. And then the main downdraft region over here. In a rotating thunderstorm, in a supercell thunderstorm that produces almost all of our tornadoes and the vast majority of our, you know, large hail reports, damaging wind reports, the updraft is going to follow the downdraft part of the storm. So if you don't have radar, if you don't, you know, have any way of getting our warnings, if you're watching the storm, you know, you see the updraft here, you see the main dark downdraft region over here, probably assume the storm's going to move from left to right. And in this case, that's exactly the way it's going to go. Maybe even move away from you into the screen here. But note where the spotter's located. You know, he's a couple miles away from the updraft, you know, downdraft. I think this is a little bit of a maybe hook echo. We talked about rotating back around the storm there. But he's a couple miles away. The storm's moving away from him, but he can still spot the updraft base right here and any potential features with this storm. Or, you know, so you can still keep your distance and have a good view with a lot of these storms. So where's a safe place to be around these potentially dangerous thunderstorms? Remember that radar image we showed of the Moore, Oklahoma tornado? Well, here it is again on the left. It's moving off to the northeast right here. So this whole storm's moving this way. Again, remember, we're most interested in this hook region right here, where the updraft is and downdraft regions are wrapping around each other. You can actually see, again, radar sees rain and hail, so all the color on the radar image is the downdraft. You can see our main region of downdraft in the main body of the storm there, and then how it wraps back around the updraft region to the left there. So a couple locations here. Point A, you know, you're closest. You probably have a really great view of the tip of that hook, any potential tornado, but you're also right in the path of it, which is a very bad place to be. So again, if you're at home, you can't avoid it. You just have to go to your shelter. But if you're able to move your location around, very bad place to be, right in the path of that, you know, that updraft, downdraft region of the storm where that hook is. Find a better spot. Point D, you know, you're behind the storm. You're totally safe from this one. Keep an eye on any other storms maybe off in the distance coming your way, but storm's moving away, you're totally fine, but you just can't see anything. You're just going to see a solid wall of dark rain in this downdraft and not be able to see the updraft region over here. So you're safe, which is great, but you're not able to help us very much by spotting. B and C are kind of the best places to be. B is probably the ideal spot. You're, you know, a couple miles away to the right of the updraft region. It's going to depend on which way the storm's moving, of course, but if you stay to the right of the updraft region, a couple miles away, it's a good place to be. Base of the storm is paralleling your where you're located. You want to stay a couple miles away in case it does, you know, start to move a little bit in your direction. These things do make some deviant motion, but if you have a good escape route or a good place to shelter, you can easily adjust if it does start to move your direction. Point C, you're even safer. The storm is definitely moving away from you, but you know, you might not know how much rain is in this wrapping around the updraft in this hook part of the storm. Sometimes these are pretty clear, you can see through them. Sometimes they're a solid sheet of rain that wraps around the updraft and enshrouds a tornado completely where you can't see anything. We call those high precipitation supercells. There's a lot of rain falling out of them, wrapping around the updraft and the potential tornado. And we did a lot of those in this part of the country, unfortunately. So sometimes we can have some hard to see storms, just a lot of rain. Squall lines positioning, A, B, C, or D, where's the best place to be? Well, there's really no good place to be. Like we talked about, these pretty much cover the entire horizon. Like there's just going to be potentially damaging wind, really all along this long line of storms. You'll probably see the shelf cloud all along this line of storms. There's really, you're just going to get hit by it eventually, and you're going to have most likely strong gusty winds as well. So hopefully you find your shelter as that shelf cloud approaches and moves overhead. You might, if you have a sharp radar eye, you see a little bit of a little like hook right here on this part of the storm. That actually is an example of one of the times we can get a tornado in this long line of storms. This was from a couple years ago in September, actually, quite a few tornadoes across this part of the state. We don't expect you to look at a radar and know that, but if you do see like the long line of severe thunderstorm warnings and then a tornado warning in between them, point B is obviously a much more dangerous spot to be in than A, C, and D. But again, just know that if you see this shelf cloud approaching towards you, you're going to get hit by it no matter where you are. So really, give us a report, but make sure you have your safe space easily accessible, or you're able to, find shelter in your car or something like that. If you stay at home, that's great. You can give us great reports. But if you're a mobile spotter, you're able to move around a bit more, follow the storm a bit. But it's more dangerous, right? You're dealing with low visibility from heavy rain, from blowing dust. Sometimes the storm itself is distracting. Hopefully you're not trying to drive and look at radar and use your phone at the same time. Please, 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 if you're going to do mobile spotter, pull over to the side of the road and stop completely before giving us your storm reports. But it can be dangerous. So, make sure you have an escape route. Usually try to park at an intersection so you have multiple road options to use if that storm does start to move a little bit closer to you. This is my paranoia. I put it in here, but keep the engine running, keep the window down, keep the doors unlocked. I just don't want to deal with locking my keys in the car ever. So that's a personal note there. Follow any closed roads, of course. But also try not to follow a wall cloud into downtown St. Paul there. It's not going to be able to keep up with it. So please keep any mobile spotting to the more open and rural areas. Not going to make it far during Twin Cities rush hour, at 5 p.m. We said visibility. It can be hard to see these updraft, downdraft features. When I talked about the high precipitation supercell, where all that rain is actually wrapping around, the downdraft starting to wrap around the updraft region, and it shrouds any potential wall cloud or any potential tornado. That's what we're looking at right here. In this picture, you're looking right at the longest tracked tornado in Wisconsin history. This thing was on the ground for 80 plus miles. And it looked like this almost the whole time. We have almost no real pictures or videos of this tornado because it was just shrouded in rain. You couldn't see anything but the dark downdraft. Getting closer is not going to give you a better view either. So just maintain your safe distance from the updraft, and maybe if you watch it longer, visibility might clear up. And then spotting at night is very difficult as well. Just hard to see any features when you only have lightning to illuminate it, and we'll show that in this video here. So note, storm, it's night, all we can see is from lightning. What are we looking at right here? Is that a funnel? Is it a wall cloud? Is it rotating? Is it moving towards us, away from us? It's kind of hard to tell when you just have little, strobe light flashes of what you're looking at. So you really have to be more careful at nighttime. Mobile spotters, just make sure you're staying in one spot and just kind of staying there. And then, giving that storm plenty of space, maybe just calling the spotting off once the storm moves away from you. Just really hard to follow a storm at night and keep up with it while driving. And if you're at home, make sure you're going to your shelter if you see any signs of that storm moving closer to you, or if you're hopefully on radar, you see that storm moving closer to you. So last part, getting your information to us at the Weather Service, basically reporting what you see. Please remember to watch the storm. Don't just look out the window, get on the phone with us. Watch, see how it evolves over time. So what are we looking for? Well, tornadoes, obviously, we want to know about those. Funnel clouds, that visibly rotating wall cloud, that's really the first kind of reports we like to get, because that's usually we can get a lot of lead time on a potential tornado when we get it in the visibly rotating wall cloud stage. It usually is going to take a couple minutes for that rotation to really pick up and increase and eventually produce a tornado. For wind, it's really wind damage or measured wind. If you're actually able to measure wind at your home, like maybe a personal weather station will definitely take your wind reports greater than 50 miles an hour. But with wind damage, usually if a storm's strong enough to be severe, it's going to do some sort of wind damage, blow some branches down, maybe some, light structures or roof damage. It's just so hard to guess how strong winds are by standing outside, licking your finger, putting it up into the air. We're really bad at it. We always overestimate how strong the winds are. So really, unless we have a measured wind speed, it's the wind damage we're looking for. Hail, really all sizes of hail help us, but especially anything greater than 1 inch in diameter or quarter-sized hail, that's our threshold for severe thunderstorms. Flash flooding we'll get into, and then of course any fatalities, injuries if known. That's usually more from, emergency management and other agencies. So hail, please measure it if possible and get a ruler out or compare it to common objects. You see that chart on the right there. Typically, the small stuff is our, U.S. currency and maybe some small vegetables. Once we start talking sporting goods, though, ping pong, golf ball, baseball, that's the stuff that really causes the damage. So anything greater than 1 inch, so anything from quarter-sized and larger, severe hail, we really, really need to know about. Smaller stuff can help us out as well, especially, if it's like more of like the penny to nickel size. It can help us calibrate our warnings we're putting out. No marbles. We don't know how large your marbles are, so please try to measure it or compare it to these, more common objects here. Give us the size of the largest hailstone you see. So, just don't. A range can help, but really we're looking for the largest size hailstone as the report you give us. Something like mostly nickel size hail, but a few to quarter size is a really good report. And then don't guess. Please just get a handful of change or a ruler, just something you can compare that hail size to. Wind, we're looking for wind damage again, not estimated speeds, and kind of in the order of severity. Any damage to structure, very important. Down power lines, that brings a whole other risk with it. But then maybe trees that are snapped or uprooted, and then eventually down to individual limbs down. Typically, when we're talking like severe wind, you're looking at about 3 inches in diameter for the limb size. So like little twigs we don't need to know about, but think about how 3 inches in diameter. When you start needing to having a wheelbarrow to move stuff around versus just pick it up in the yard, that's maybe a rough threshold for severe wind versus maybe some not as severe wind. So flooding, certainly I've had a lot of this to deal with the last couple of years. Really, how deep is the water, and then how is it flowing, or is it just sitting there? Flowing water is much more destructive than water just sitting there. Don't walk into the middle of the water and measure it. That's not a good idea. Stay out of the floodwaters. But is it over the tops of curbs? Is it getting over the tires on cars? Over the fire hydrants? Good reference points like that. And then if it's flowing or just sitting there ponding. Impacts are probably most important when it comes to flooding. Are there any structures that are flooded? Any streams coming out of their banks? Roads closed or even washed out? And then kind of, every town has the spots that flood during a heavy rain. It kind of gets underwater a little bit for maybe an hour, and then the water goes back down. That's kind of the lowest urgency. We usually don't put out flash flood warnings for that kind of flooding because it's just kind of typical routine stuff with a summertime thunderstorm. Turn around, don't drown. Please do not drive into floodwaters. Stay away. And then finally, spotting, just kind of quick here. Storms can look confusing, so be wary of lookalikes. The steer-looking clouds I talked about earlier. This right here looks a lot like a funnel cloud, but if you watch it with time, it wasn't rotating. It didn't last very long. It wasn't really attached to the updraft base. Rain shafts too can look maybe like a tornado or something also. But if you watch it with time, try to find the updraft, try to find the downdraft, look for rotation. That'll really tell you what you're looking at. So getting the reports to us here, a lot of different ways to do it. If you're part of a spotter group, like a spotting network or fire department or something like that, go through their local protocols. But you can send reports to us as well. There's spotternetwork.org, which is a great resource for storm spotters. Can send reports in through them. We like reports on Twitter if you're into the social media route. Twitter gives us everything in real time, where Facebook can be, who knows when we see it with all the algorithms and stuff they use. So if you do at NWS Twin Cities or use the hashtags MNWS or WIWS, depending on what state you're in, we just see those reports more in real time. And if you have pictures, send them to us. The pictures really help us. Again, we could retweet or share the report you gave us, and then other people can see that picture of wind damage in Fairmont there. And again, people see a picture, they take that threat as more serious than if it's just, the Weather Service, yelling at them again. We do have a spotter phone line to give us phone reports. It's an 1-800 number. I'll have it up at the end as well, but it's 1-800 if you want to reach us by phone, to phone in reports. Really, whatever is most efficient for you. You can also go through our website, our weather.gov/Twin Cities. On the left there'll be something that says current hazards. Underneath that, submit a storm report. And from that form, you can just click submit a report right there. It'll, ask you different questions, what you're looking at, what kind of wind damage is it, how big is the hail, kind of a form like that will get those reports to us. But if you're using social media, watch out, or we have to watch out for hoaxes. People just like to do this. This guy gets around. This picture that's shared anytime there's a tornado somewhere. It's been Hurricane Sandy. It's been Hurricane Matthew. It's been a lot of things. This one, anytime there's a tornado in the Midwest, someone tries to tag that as the current tornado. So, please. That's why we take our storm spotters so seriously, because we know we can trust you by getting reports from our storm spotters. If it's just, someone sharing it on our Facebook, we might need to do a little bit of fact checking. And so it can definitely lead to some misreporting, unfortunately. So a couple really quick example reports here. What would you report here? Well, we have hail. You want to let us know what time that hail's occurring at. If it's occurring right now, that's best. But if it fell 10 minutes ago, you can let us know that as well. And then measure it, right? She has a ruler out, which is great. So let's say our largest hail is about maybe 3 inches here. So definitely large hail. Say the largest stones are 3 inches. Other stones ranging from, maybe 1 to 2 or however large these were. Good report. If you want to send it through social media, that's great as well. It's from our broadcast meteorologists down there. So this is from Albert Lee, and he just sent us a report of, kind of typical low water street in town, goes underwater during a heavy rain most of the time. So we get this report. Maybe we were worried. Maybe we think we need a flash flood warning. We see that. We know, okay, it's just your typical rain. Probably hold off on a warning for now. Don't need to do a false alarm. So those reports can help us as well. This one, we have wind damage. So we're not going to try and guess how strong these winds are, but we can report, hey, we have power poles snapped at, whatever road this is. Maybe we're at, I don't know, Audubon Road and, near the Caribou Coffee in Chanhassen, Minnesota. And we can give a location. Maybe I'm 5 miles west of Hastings. You can give a location, which helps us out tremendously as well. What time? Maybe you're just driving across. Maybe you're just coming across this a couple minutes or even an hour after the fact. Tell us what time you're seeing the damage. Not, oh, I think it happened now at this time. We can go back to radar and compare when maybe the strongest part of that storm hit that location and get the time from that. Last one here, we were looking at a wall cloud, and if we can't tell in a picture, but it's rapidly rotating, visible rotation right here. So we could say, hey, I'm watching a visibly rotating wall cloud, which is a report we want to get. It's happening right now, and I am 4 miles southwest of Fairmont, and no funnel or tornado at this point, but I'll let you know if the storm continues to strengthen, the rotation gets stronger or anything like that. 5 minutes later, you call the weather service back. Hey, it's me again. I'm in the same location, southwest of Fairmont, currently happening. I now have a funnel cloud, and I can't tell that's a tornado. I can't see anything on the ground. So rotating wall cloud has now formed a funnel. I'll call you back if I see any signs of that circulation on the ground, right? Or maybe you stay on the phone with us or give us another report a few minutes later, and eventually you see that tornado circulation on the ground. And so kind of that strain of reports there is really useful to us. Because maybe this funnel dissipates and it lifts back into the storm, and then we know the threat is maybe subsided for a little bit. So that's the severe weather spotting side of things. We also will we love to get your reports with rainfall or especially snowfall in the wintertime. Not severe thunderstorm related, but just as important to us. Our main way of getting these reports from citizens is from what's called COCOROS, Community Collaborative Rain, Hail, and Snow Network. So if you go to this website, there's plenty of information. You can sign up for it, get a rain gauge from them. Can't remember exactly how much it is, but it's like $20. And then you can get the app at the website, submit your rainfall reports, submit your snowfall reports to us. Whenever you see those snowfall reports or the snowfall maps we put up after a heavy snow event, a lot of that comes from COCOROS, from our COCOROS observers giving us reports, and it helps us fill in the map. So maybe get a competition going at your workplace or any group you're in at school and see, who gets the most snowfall at their house with each storm. Sign everybody up for it. It'd be a great idea. And then finally, last but certainly not least, is our Weather Ready Nation Ambassador Program. This is for organizations, schools, businesses, groups, sporting teams, volunteering organizations, not individual people. So this is maybe an organization you're part of. You can sign up for this, weather.gov/WRN. A lot of great information here, how to sign up. Really, you help us support weather preparedness. Just like talks like this help support weather preparedness. We give you resources. You share those resources with your group however you see fit. Maybe you put our graphics on social media. You retweet some of the things we post. A lot of different ways to be involved in this. So please see our website there. Just a couple examples of who we have signed up. All over the place. City government, science museums, large corporations like Hy-Vee. Anyone can get involved in this, any group, organization, school, business, you name it. So if you're interested, please either, ask us questions, send us an email, or go to this website for more information here. So just additional training. We'll send an email out after this presentation with this. Actually, we won't do that in Facebook Live. Sorry, we won't. But here's some additional information here that you can get if you want to learn more about storm spotting. There's also a few other NWS office training courses on YouTube you can check out. But that's it. Hope this went smooth for everybody. Just remember, storms are incredibly dynamic. They're always changing. So just sit there, watch them, see how they evolve with time. Always stay safe. That's our number one priority. We don't want to get a report from you if it's a risk of putting you in danger. So make sure you're safe. Make sure you're watching the storm, and then reach us at any of the ways down here. However, your most efficient way to get those reports to us. So I think that's going to be it. Yeah, and you can still continue to ask questions, I think, on our broadcast here, even after the presentation ends. If you're watching this at a later time, I think you might still be able to ask questions, even if it's a couple of days after the fact or months after the fact, and we should be able to see those on our social media accounts as well. So thank you, everybody. Hope you learned a little bit here tonight, and have a good evening.